Hello and welcome. This is Seung and I am the director of Sky Academy, and if you've made it this far, it's because we've finished and gone through each of the episodes in Geometric Applications of Calculus. So now what I would like to do with you is to share a little bit of a summary of what we went through, yeah? So I'm gonna go step by step through what we covered in that video. So let's do that now. All right, so we started off geometric applications of calculus by looking at the fact that the derivative f dash of x of a function gives us another function, which is what we call the gradient function. Yeah, so the derivative gives us the gradient function. Now, what is the gradient function? It basically is another function that allows us to find the derivative, or the gradient of the original function f of x at any point along the x-axis, right? So in other words, if we want to find the gradient of f of x at x equals to 2, what we have to do is find the derivative, and that gives us the gradient function, substitute in x equals to 2, so we're looking at f dash of 2, and that'll give us the gradient of the tangent to the original function at x equals to 2. And I say that the gradient of the tangent because if you actually examine it, the tangent is a line that will have exactly the same gradient as the curve at that particular point at x equals to 2. Yeah? So in other words, the tangent is a line that shares the same value for the gradient as the curve at the point of contact, right? Which is what we have to do, which is what we have to realize. So the gradient of a tangent to a curve y equals to f of x is given by the derivative f dash of x, and by substituting in to f dash of x, right, the derivative, the value of x that we're wanting to find the gradient of, okay? So yeah, so we looked at the gradient of the tangent, and then in a later episode what we did was we looked at how to find the equation of a tangent, okay? Now basically the equation of the tangent, well, we know this. We know the gradient of the tangent will be f dash of x at the value of x that we're finding the tangent for. So the value of x at the point of contact. And we know to find the equation of a tangent, we basically use the point gradient formula for a straight line, because after all, the tangent is just a straight line, right? So that's what we do. We go, we use y minus y1 equals to m outside of x minus x1, where m is the value of the gradient given by the derivative substituting in x1, okay? x1 being the x coordinate for the point of contact, which means y1 will be the y value for the point of contact. So you've got the x coordinate and the y coordinate of the point of contact. You've got the gradient given by the first derivative, and you use the equation y minus y1 equals to m in brackets x minus x1 close brackets for the equation of the tangent. Yes? For the equation of the normal, right, you do exactly the same thing. You recognize that a normal is just another equation. Yep. Again, it'll have the point of contact x1 and y1, but this time the gradient, rather than being equal to the derivative at the point of contact, it's going to be the negative reciprocal of the gradient at the point of contact, because a normal is perpendicular to the tangent and we need to account for that perpendicular aspect. So in other words, m1 times m2 equals to minus 1. That's the rule for perpendicular lines, yeah, or perpendicular gradients. In other words, the gradient of the tangent will be 1 on m2, right? So 1 on f dash of x1, yeah, which is basically what I'm trying to say. Yeah, so we've worked out the equation of the tangent and the equation of the normal. Now, the other thing that we looked at, or the next thing that we looked at, was the whole idea of stationary points. Now, the special thing with a stationary point is that the gradient will be flat, totally flat. Okay, so you've got a flat gradient, which means that the gradient will be equal to what value? Yeah, the gradient will be equal to 0. In other words, f dash of x, which represents the gradient, will be equal to 0 as well. Okay, so in other words, that is how you find stationary points. Right? The next thing that we have to do is determine the nature of the stationary points. And there's 3 types of stationary points. There's maximum, minimum, maxima, minima, and horizontal points of inflection, which I'll go through later. All right. So basically, what we went through in that particular episode was we looked at how to determine or work out the stationary points. You basically just equate the gradient function to 0, and you work out the values of x that will solve that, and that'll give you the x values of the stationary points. You substitute into the original formula to give you the y values, okay, or the y coordinates of those stationary points. Now, I did talk about number 1, being able to find the stationary points, and then number 2, being able to determine the nature, whether it's a maximum, minimum, or horizontal point of inflection. And what helps us to do that is the next concept that we looked at, which was the second derivative. Now, the second derivative is basically just the derivative of the derivative. So you're differentiating twice, right? So you've got f double dash of x, which is your second derivative. And why is the second derivative useful to us? All right, because you can continue to find the derivative until you have nothing left, right? So you can find the third derivative, fourth derivative, fifth derivative until you have nothing left, but we tend not to do that. What we do is definitely we use the second derivative because it's important in telling us the concavity, right? Concave up or concave down. Now, concave up is basically, if you've seen like a parabola, concave up is a smiley face. Concave down is a frowny face. So second derivatives, right, actually help us in that way, which allows us then to have a look at how we can apply first and second derivative to special points on a curve, right? So basically, there are 4 points on a curve. You've got maximum, minimum, horizontal point of inflection, and regular points of inflection. All right, and those 4 points are actually special. They're useful for us in curve sketching. Now, we looked at maximum and minimum points, and basically what we worked out with maximum and minimum points is that the first derivative will be equal to 0, and that the second derivative will be negative in the case of a maximum, and positive in the case of a minimum, right? What you also have with maximum minimum is a sign change for the first and derivative on either side of the curve. So remember that. And then what you also have is that for the second derivative, there won't be a sign change on either side. And maximum minimum are a special type of stationary point called a turning point. Right? The other type of stationary point is called a horizontal point of inflection, which is part of the family of what we call points of inflection, right? And what separates a horizontal point of inflection from a regular point of inflection is that a regular point of inflection isn't a stationary point. It's not a stationary point, and therefore the first derivative is not equal to 0. But what's common to points of inflection is this: there will be a sign change on either side of the concavity, because a point of inflection is by definition where the concavity changes. You're going from concave down. See, this part of the curve is a frowny face, but this side of the curve is a smiley face. Yep. You've got concave downness going to concave upness, or concave upness going to concave downness. And that's the same whether it's a point of inflection or a horizontal point of inflection. And in terms of algebraically speaking, how that's represented is that the second derivative will be equal to 0, and there will be a sign change on either side of the second derivative at that point of inflection, which is what makes it a point of inflection in the first place. In terms of the sign change for the first derivative, then there won't necessarily be one. In fact, there won't be one. Okay, but for a horizontal point of inflection, the first derivative will be equal to 0. For a point of inflection, it won't be. All right, so that's a useful summary for points of inflection and stationary points, so that's really useful. After that, what we did was we looked at maxima and minima, and we looked at the difference between what we call global or absolute maxima minima and local or relative maxima minima, right? And we worked out that a local or a relative maxima minima is basically one where you have where a maxima minima behaves the way a maxima minima would or should in terms of it being a stationary point and in terms of there being a concave upness or a concave downness to the curve, right? So in other words, it'll be where there's a stationary point and where you've got a turning point essentially, right? So that is what we call local and relative maximum minimum, and sometimes local and relative maximum minima can be absolute and global, but sometimes they might not be. And that'll all depend on the domain that you're looking at for a particular function. So you've got to be clear about the domain of a function, and then the global or absolute maximum would be the highest point of a function in that domain. The minimum, the global or absolute minimum, will be the lowest point of that function within that domain. Does that make sense? Which may or may not be a relative or local maximum minima. We just don't know, okay? We also then looked at, equations of tangents and normals, which we went through. We looked at primitives and anti-differentiation, which is basically the reverse of differentiation, right? So we looked at the reverse of differentiation, and we worked out that the reverse of differentiation gives you what we call a primitive, which is denoted by capital F of x. And if you differentiate the primitive, you get the original function. So it's the reverse process of that. And the way we do that is we basically add 1 to the power and divide by the new power, okay? So we did that. The next thing that we did was we looked at maximum minima problems. We worked out that yes, we know how to find maximum and minima on a curve, but that allows us then to find maximum and minima quantities in word problems, yeah? And there was that 4-step process that I went through. So go back to that episode if you want to be clear about that, but just to refresh your memory, for maximum minimum problems, this is the 4 steps that you really need to go through. Step 1, you've got to read the question. If at all possible, draw the diagram that represents the problem. And then what you got to do is find or determine the variables that you're working in. One's going to be your independent variable. The other one's going to be your dependent variable, right? And you need to, there's only 2 variables that you need to be able to reduce down the formula to, so that you can set up the formula. And that's step 2. You set up the formula, and then once you've set up the formula, you work out the maximum and minimum points, or the maximum and minimum values, and then the nature of those maximum minimum values, right? So to work out the maximum minimum values, you basically make the first derivative equal to 0, and you solve for your independent variable, okay? You've got to find the values of the independent variable that make the derivative equal to 0, and then you determine the nature. Okay, and by determining the nature, there's 2 ways of doing it, right? You either work out the second derivative to work out the concavity, right? Whether it's a maximum or minimum, whether it's concave up or concave down, or you can test points on either side of the first derivative. And it just depends on the question, right, as to which one you use. Sometimes finding the second derivative is really messy and really ugly, in which case you use this one. Other times, testing on either side of the derivative can be really ugly, and the second derivative might just be a much simpler option as well. So it's up to you which one you use. Oftentimes the question will tell you, the question won't tell you, but oftentimes the question will give you an indication of which one will be the easier one to use. And finally, you've got to answer the question in the given variable, which is where a lot of students stuff up, might I say, because they, the question might say find the maximum area, and they'll give the maximum width that gives the maximum area but not give you the maximum area. Other times it's the other way around. They'll give you the maximum area when they're looking for the width. Yeah, so basically you need to be able to answer the question in the given variable. And then lastly, what we did was we basically applied maximum, minimum points of inflection to help us with curve sketching different curves, right? Sketching different curves. And that is basically a really, that was quite a thorough summary of the unit of work on geometric applications of calculus. So there we have it. That is a summary of that chapter. Let me stand to the side and you can take that all in. Thank you very much for watching. In the next chapter, we'll be starting integration. Thank you for watching. Bye.